Okay, so hi everyone. So welcome back to the workshop. So my name is Tachapo Saranura. I will talk about like two things. One is the what is witness of length constraint expansion. Another thing is low step flow emulator. So let's start. Let's see. Okay, so this talk, the goal is for you to get like a more clearer picture of this theory, right? And I want to stress like the why we study this again, like just to repeat what Bernard just said. When we talk about graph problem, even if you care about graph problem that concern about just congestion only or distance only, you just care about this one of these two, but end up when you try to solve it, many times it turns out that you need to care about both congestion and length at the same time. And this is why this theory, this is something that like we are so excited about. Okay. So, but for this talk, you will learn three core concepts. First is the witness of length constraint expansion. Another is what is witness length constraint expanded decomposition. And the last one is low step emulator. So the first two part is something that kind of already appear in Bernard's talk, but the hope is that once you see this notion of witness, the hope is when you think about what is length constraint expander, you will get like some mental image that okay, with the notion of witness, you have some mental image that you can just see immediately what is this object. So it's like a bit clearer what is this thing. Okay. And this low step flow emulator is another structure that is like a core object that we will use throughout the workshop. And that's why I tell you about this. Okay. Then just to recap, I need to tell you a bunch of definition before going to these three concepts. I need to tell you again about what is flow-based definition of length constraint expander. And in this talk, I will use the words expanding and routable interchangeably. So when the graph is expanding, it just means that the graph is really good router. And if the graph, what happened? If the graph is really good router, then it's expanding. So expanding is just cut view, and routable is flow view. Okay. So a bunch of basic definition. So everything in this talk, the graph is undirected. The graph will have edge length, and just for simplicity, it has unit capacity. Everything works with capacitated graph. And so there's going to be some edge length like this, the red number here. And when we talk about multi-commodity flow, concretely, this is just a function that assign value onto paths. Like here, you have like you assign value 1 into this path, value 0.5 to another path, value 1 to another path here. Okay? And the congestion of the flow is the maximum flow value on any edge. So for example, in this flow, the congestion is 1.5 because this edge you have 0.5 and 1 here. Like this congestion here is the maximum congestion. So 1.5 here. And step of the flow is the maximum number of edges in any flow path. For example, in this graph, in this flow, it's the green path here that takes like maximum step, which consists of I don't know what happened, which consists of 3 edges. And length, we count the maximum total length on any flow path. And the length of this flow is 7. Why? Because of this pink one. The pink one have length 7 because of 5 here and 2 here. Okay, so it's important to distinguish between length and step. Step is about number of edges. Length is just count sum the total length on the path. Okay. And we said that the flow route a demand D if like for every pair AB, the demand AB is just the sum of flow value from A to B. For example, this flow route the demand from A to B in total of 1.5 because of this 1 here and 1.5 here. So from A to B is 1.5 and from X to Y is 1. And usually it's nice to think of the demand itself as another graph, another undirected graph, like this graph. So there is an edge from A to B with capacity 1.5 and X to Y with capacity 1. So just think of D itself, the demand, as another graph. And once you think of D as a graph, then you can think of F as an embedding of D into G, right? So we said that the flow F embeds the graph D into G. That's what I mean by embedding. So when I say that D can be embedded into G, it means that the X is a flow that route demand, that route D into G. Okay. And by the way, like just ask question when something is not clear. Okay. So next, demand. Okay. I said that this demand, when I say demand D is H length constraint. If I just try to route between pairs that have distance at most H. So demand is non-negative. Only between the node AB whose distance is at most H. That's when I said the demand D is H length constraint. For example, this demand D is H length constraint because I only try to route between the pair that are close, not between like the guy that are far away from each other. And we said that the demand D is A respecting for some function A if the total demand that you want to route between from any node is at most A of B for every node B. For example, this demand, if I set the purple node to be set S, and let's set the function, the indicator function of the set S is 1 sub S, then this demand is 1S respecting. Because for every node here I want to route 0.5, here I want to route 0.5. So basically the degree of D is at most 1 for every node. Okay. So that's just a definition. And in general, I just call this function A a node weighting. Okay. So, and node weighting, you can think of it as like indicator of some set, but it can be something else. It can be the degree profile of some graph or something else. And the size of A is just the sum of A over all nodes. Okay. So now, last definition. When I say that the demand is routable, it just means that there exists a flow that route that demand. What do I mean by the node weighting is routable? The node weighting A is routable. Here I mean something quite strong. I mean that every A respecting demand is routable. So if A is routable with congestion something, length something, and step something, then it means that this node weighting for every A respecting demand is routable with that congestion, length, and step. Okay. And if A is H length constraint routable with some slack S, it means that for every A respective demand that try to route only between the pair that are like within H distance, like it's only like length constraint demand. For every A respecting H length constraint demand, you can route it with length basically H, but with some slack. So the length is HS. Okay. So just so that you get make sure you get definition. Suppose that the graph is a path, right? And A, let's say it's just all one, like just one on every node. Then okay, A is not routable with congestion less than n over 2, because if you have a path, then you look at the demand that try to route the first half to the second half, then this demand is not routable. The exists demand that A respecting, and the congestion here is big, n over 2. But in this graph, A is, let's say, A is length constraint routable with length slack just 1 and congestion just 4. Why? Because, okay, when you just look at demand that is length constraint, well, the demand is only between like a node with distance at most 4, if it's 4 length constraint. Then if you look at any edge UV, then the total demand that can cross any edge UV in this path is just going to be at most 4. So the path is not really good, like it's not really routable when you talk about long demand, but when you restrict the length constraint, you have a length constraint and the demand, then it becomes good, just like what Bernard has said in his talk. Okay, so the congestion here is still going to be at most 4. Okay, so with this, now we can say precisely using the definition that we just said, what is length constraint? What is expander? Well, just normal expander, the graph is phi expander. If I take this as a definition, okay? It's equivalent to the cut definition, cut-based definition. The graph is phi expander if the degree node weighting of the graph is routable with congestion 1 over phi. What about length constraint expander? The graph is HS length constraint phi expander if the degree node weighting is H length constraint routable with length slack S and congestion 1 over phi. So any length constraint demand can be routed with some slack and congestion 1 over phi. And here, phi, you should think of it as like 1 over phi here. Think of it as polylog or n to the epsilon. It's not constant here in this talk. And okay, A is length constraint phi expanding if the same thing, but replace length constraint degree node weighting here by A. Okay. And just to make sure that you listen to Bernard's talk, can you tell me which graph is not the length constraint expander? Number 3. Correct. Thank you. Yeah. Okay, so this one is the length constraint expander. This one is not. And this one is still length constraint expander, because even though there is like a lot of, like there can be this click here, there are demand that are far away. So when you look at length constraint demand, there are no length constraint demand between these two. So this is still length constraint expander. Okay. Okay, now we are ready to talk about what is a witness of length constraint expander. Just to recall, A is length constraint routable or expanding. Yeah. The definition was that it's about for all definition. Every irrespective demand that is length constraint is routable. Okay. But what we want is something that about existence of something. We want to witness. We want to know like a clear mental picture that we can think of it instantly, right? What is the certificate of this thing? So it turns out that thing is just embedding of router on a cluster of edge neighborhood cover. So let me be clear, what are these two terms? Okay. So first, routers. So I said that a T-step router is just a graph. I call it R. T-step router R for a node weighting A is a graph such that its degree profile basically is A. Let's say within constant factor 2. Okay. And now it should be that anything on A, like A is routable inside this router R with congestion 1, so no congestion, and step T. Okay. That's when I say graph is T-step router. And it looks strong, but for example, if the graph is really well connected like a click, then it's a good router. So let's say you have A, and then if you take a click and you scale each edge properly according to A, then you can say that it's a two-step router. Let's see the example. If A, let's say, is like a indicator of some set S, so A is think of it as a subset S. Okay. Then if you take the click and scale the capacity to be like 1 over S, right? Then when you want to route between any two nodes, you can route it. And instead of drawing this click, throughout the talk, I will just draw a star here. Star is a two-step router, except that it has like kind of one more node. So if you don't allow that, then you just use a click. Okay. And the star here has capacity 1. And let's see why intuitively why is a two-step router, right? Suppose I want to route from B to C. In the click, I can just route like send 1.1 over 5 fraction of flow or 1 over 4 through everyone, and then send from B to C. Okay. And I can simultaneously route from A to D. Okay, and in star I just do it. And if I want to route simultaneously from A to D, also just from A, just send to everyone, and then to D. Okay, so the congestion on every edge here will be like basically just use like twice. Yeah. So as long as the demand is like is A respecting, then the congestion on every edge is basically 1. Okay. Okay. So click, there is a router that has low step. Click is one example. When you care about algorithmic applications though, click is too dense. We will need sparser graph. For this talk, click is okay because I was just gonna tell you about existence proof. When you need a sparser graph, you can use some sparser graph like a power of a hypercube that would work. You get some trade-off between the step and the sparsity of the graph. But for this talk, just think of it as a click. Okay. And I represent it with a star. Okay. Then edge neighborhood cover. We have seen this, but let's see some picture. So first, clustering. I need to tell you, clustering is just a disjoint set of clusters or vertex subset like this, just a bunch of disjoint subset. And an edge neighborhood cover is just a collection of clustering. So not just one disk of like not one clustering, but several clustering on top of each other. And for every node V, if you look at the ball around it of radius H, then there must exist some cluster that contain that neighborhood completely. So that's when I say this is like a neighborhood cover, edge neighborhood cover. So any edge neighborhood, there's some cluster covering it. Okay, so we see what is router, what is neighborhood cover. So now we are ready to tell you what is witness, like length constraint routability or expansion witness. Okay, so edge length constraint routability witness of A consists of first the edge neighborhood covers like this. So there are more clusters, but I just draw some cluster kind of already cover A. Okay. And not just that, then for each cluster, you have a router for that cluster. For each cluster C, you have router RC, which is a two-step router on A intersect C, where A intersect C have like normal expected definition, just A restricted to C. Okay. So like this. So just kind of anything that you want to route on A inside this cluster, there is a router that associates with it. You have this router for every cluster. And then the last part is the embedding. You can embed all these clusters simultaneously into the graph. So it embeds all the cluster, the union of this cluster into G. And this embedding should be good. In what sense? Both length and congestion. The length of the embedding or the flow, like the flow that embed this router should have length at most HS. S is the length slack, and the congestion should be 1/5. Right. So this is what you think of length constraint expander. Just you have neighborhood cover, and you have router on top of it. Then and all of this can be embedded into the graph with good length and congestion. Okay. So this really is an equivalent concept with like the graph, the node weighting is routable if and only if there exists a routability witness. Okay. It's almost the same with just some slack. If there exists the routability witness, then it's routable, and vice versa, but with some slack. And the slack is basically kind of small. Like you have 2 here, you have like S square here, and something here, like n to the 2/s. And you think of this as something small still, because you think of S as a big constant. Okay, so that's witness. And now what is witness? Expanded decomposition? Well, just to recall you, what is expander decomposition? So Bernard talks about moving cut or length constraint cut. Moving cut and length constraint cut is just the same thing as to do length increase of edges, right? So a length constraint cut, HS length constraint cut, is just a function that assign number like fractional value into each edge, like from 0 to 1, and it's a multiple of 1 over HS. And if you look, and this is definition, the length of the graph after you apply this length increase or C, okay, it's just the length of HE is just the length of the graph increased by the cut size times HS. So if this thing is 1 over HS, then you increase it by 1. If C of E is 1, then you really increase it by HS, which is intuitive, like morally, it means that you have cut that edge because it's kind of far away from by more than like the endpoint is far away by HS distance already. So morally it's just to cut that edge. That's why we say it's length constraint cut. Okay. So now that I recall what is moving cut or length constraint cut, now we can talk about expanded decomposition. So for any node weighting A, right? Suppose that if A is routable, then there is a witness, but possibly it's not routable. But the point is that the point of expanded decomposition is to say that still you can always find some cut or length increase that increase each edge up to HS, like in length, like you increase the length of some edge like that. And then after the length increase, then A become routable. A is length constraint routable with some slack after length increase. Okay. So imagine that like there might be some like kind of bottleneck here, right? But it's short. But now like you might just increase the length here. So now there are like the demand, like there is no demand between these two cluster anymore. And then it becomes length constraint routable. So the neighborhood cover after length increase, now they are like separate. So just increase the length a bit, and then A become routable. And the size of C is basically it's gonna be like proportion to the size of A over the congestion that you choose. So that's what it is. And witness expanded decomposition is just the same thing, except that you just return the cut, but not just that, you also return the witness of routability of A, not just to guarantee that A is routable. So you basically have the router on top of each neighborhood cover and the embedding of this router. So just to be precise, witness expanded decomposition consists of two things. Given any like some parameter and like for the node with like the expanded decomposition for node wedding A consists of two things. First, it returns some length constraint cut or length increase of some edges so that the total cut size is like 5 times A, increases the length a bit. And then it also returns routability witness of A, which is like router on top of cluster of neighborhood cover. That is how you think about witness expanded decomposition. For any graph, you can increase the length a bit, and then the node wedding that you care about is routable. After you increase the length. Okay. And by the way, like this is nice, but many times you actually want not just routability witness of A, but you want routability witness of A plus degree of C. Like degree of C is just the degree profile of node that is incident to C. If some node incident to a lot of cut edges, then that node has so yeah, degree of C of V is just sum over E that contains V and C E. So this is what we mean by boundary linked. So it's like intuition is that A is also well linked to the cut close to it. Okay. And this can be actually improved to something like 1/5 and this thing. Yeah. So you can, but it's good to have this. Yeah. The picture that you should think about is like on the router, it also you can kind of connect to the cut that is close to that. The cut and neighborhood cover kind of overlap a bit, and the router connect to the cut too. And then the qualitative number that is important in this theorem is that is here. This is like the slack, and the point is that the slack of this expanded decomposition is just something like n to the 1/s. Okay. Good. So now I hope you get like some mental picture of witness and witness expanded decomposition. Now I'm gonna talk about low step flow emulator. The reason we talk about this is that it's gonna be a core structure on like a strong application in both tomorrow and on Thursday. And you see that it really is a generalization of the well-studied theory of distant emulator or offset. And we try to make it to also preserve congestion in addition to just distance. But today you see the existence of this only. Okay. So what is this morally? Low step flow emulator is just a graph simplification that preserve mean cost multi-commodity flow. So mean cost multi-commodity flow is preserve both length and congestion. And it allows you to just focus on flow that has low step. Flow that consists of, like each flow path consists of small number of edges. So let's see a more like for more definition. I said that a T-step emulator edge of the graph G is such that for every length scale h, the following is true. Two things are true. So any demand that is h length routable in G is also routable in h with basically the same length, but with small step. Think of T as a constant. Okay? Anything in G that is routable, you can route with the same length, but with small number of edges, constant. And vice versa, anything that is routable in H is routable in G. So more formally, it means that if some demand is routable in G with congestion 1 and length H, then that demand is routable in H with congestion 1 and basically the same length, but with small step. S here is called length slack. Another direction is H itself is embedded, like you can embed H into G with congestion kappa and no length slack. So you kind of pay some congestion slack here. And what do I mean by no length slack? It just means something natural. That is, you have embedding, right? So each edge is each edge in H really correspond to some embedding into G. So if the edge in H have length L, then its corresponding embedding flow or path here has length at most L, no length slack. And by the way, this thing implies it's stronger, but it implies this, which syntactically looks similar to this statement. So any demand that is routable in H with condition 1 and H, then it can be routable in G with condition kappa and H. So you see that it really is like kind of a graph such that congestion and length are basically the same with respect to any flow. But when you have G and you construct H that is basically equivalent, now you just care about flow that have low step. Okay. So that's low step flow emulator. Okay. And we will see today that there exists a flow emulator such that the length slack is T squared and kappa is 1 n to the 1 over T for any T. Think of T as a constant. And by the way, like we, instead of focus on every edge, we will actually, you can just focus on one particular edge. So I call like edge length constraint T-step emulator. It's just the same thing, except that now I look at one parameter edge. And it's okay to look at one edge, because if you can construct this for one edge, you can just compute this for like edge equals 2 to the I for every I, and union this log n mini graph, then you're done. Okay. So I will try to tell you how to construct this thing. Edge length constraint, low step flow emulator. So, and just for explanation, I tell you how to construct this for like one node weighting A. This is actually more general, yet it's actually clearer to explain. Okay. So let me try to tell you why this exists. And the plan is to follow expanded decomposition paradigm. That is, suppose that it's expander, that A is already expanding or routable, then show this emulator. And if it's not routable, then just apply expanded decomposition. Okay. So the first step, suppose it's routable. So A is routable, means that there exists some routability witness in G, which look like this, right? Neighborhood and router and good embedding of this router with good length and congestion. Then let's take the edge of each router and set the weight to be 10 HS. If this witness is for 10H. Okay. Then the claim is just this union of the routers is already like a low step flow emulator. Okay. The union of this router, this click or a star here is a two-step emulator with some slack. Why? From the definition, like anything routable in G in H can be routed in G because you can embed the graph H into G. From the definition of witness, this router can be embedded into G with some congestion 1/5 by definition of this like congestion, like this definition of witness. And also it has no length slack because you know that the router here have length, like the embedding part here have length 10HS because it's for 10H here and the length slack is S. But we just set the length of each router edge to be 10HS. So it's just set it to be more than the length of embedding part. So there's no length slack. Okay. So on the other hand, now like you need to say that anything routable in G can be routable in H with basically the same length and small step. In this case, it's just 2 steps. So suppose like the Y is 2, it should be clear, like it's kind of route along the star or on the click, right? Then it should be 2. So let's see formally Y. Suppose that there is some flow routable in G with length H. Okay? So they are like kind of close within distance H. Because they must be, each of this flow must be close because the flow length itself is H. You know that this endpoint of the flow path must be inside some cluster, some H neighborhood cover. And because they are inside some same cluster, there is a router on top of it. So you can just route through the routers in 2 steps. Just route like this and write it. So the step is 2, and the length is just 20 HS because the length of this is 10 HS. So that's it. Like return the router, the unit of router, and you're done. In the case when the graph is routable, when A is expanding or routable. Okay. Good. So now, what to do in general case? Well, we obviously want to apply expanded decomposition. So suppose that you have this A, okay, node weighting A, and it's not actually routable. There is no witness for A yet, but we have expanded decomposition. So let's try. So set A1 to be A and repeat several times. For each time, just compute the expanded decomposition for A here, for AI with some parameters. Ignore this for now. And so what you get like some cut or length increase or moving cut, length constant cut. Get this cut. And then you have the witness after you apply the cut, after length increase. So you get like this routers on top of A. So what you do next is the natural thing to do. Just set AI plus 1 to be basically the degree profile of the cut. So the A2 here is just basically if there are a lot of cuts here, then the node weighting here is big. If there are like not too many cuts here, then the node weighting is small. So this is A2. 10S here is for technical reason, but you should maybe ignore. Okay. So A2 from the cut, you just define A2 as kind of a new terminal set that you do expanded decomposition for the next round. So you try to do expanded decomposition with respect to A2. And then you get smaller cuts. That smaller cuts define A3 and repeat. So suppose that just suppose for this picture that okay, suppose there is no cut. So that A2 is already routable. So there are just two levels. That's easy to draw. Then once the cut is empty, then you're done. Then just return. What you return you just return this union of all the routers. And set the edge length to be 10 HS on each edge of the router again. So in this picture, there are like two levels, but you can actually see that there will be at most T levels. Reason is that you can see that the size of A is proportional to the cut size, which is something like 5 times AI. Like AI plus 1 is like the cut size, which is like 5 times AI. But you can set phi here to be small enough. In this case, we set it so that the size of AI plus 1 is smaller than the size of AI by something like n to the 1 over t. So after t rounds, then it's empty. So in general, there are t levels, but let's look at this picture and let's say there are two levels. Then why the union of this router is good? Let's see why. So one direction is again easy, kind of almost from the definition. Anything routable in H is routable in G because this H is just the union of these routers. And each level of the router, you can embed them simultaneously into the graph G. So the congestion is small. It's 1 over 5 now times T because there are T levels, but T is constant. So, and no length flag with the same analysis. So this is easy. Same proof. So the more interesting case is to say that if you can route something in G, you can route in H with small number of steps. And actually there are two cases. The first case is when let's look at some demand that is routable in G, right? Suppose that this demand is routable in G like this, and it's still closed in G minus C1. Okay. Then it's basically the same like before. Why? Because you can see that if these two endpoints of the flow is closed in G minus C1, then there must exist some router containing both endpoints like before. Because this is a router, this is the witness of G minus C1. So there must, if they are closed, it's a witness of G minus C1. So if the two endpoints are closed in G minus C1, then there must exist a router containing both. Once there exists a router containing both, just route through the router in 2 steps. Okay, so this is like just like before. So the really interesting case is just when there are two endpoints here, but they were closed in G, but then now they are kind of far in G minus C1. Okay. So let's look at the picture. It looks like this: A and B, and you want to route from A to B, but now they are far in G minus C1. It's far after you've applied the length increase. So this is like the last slide on technical thing. So I kind of let's zoom into like A and B here. So it's kind of look like this. A and B is here, and there are like some cut length increase in between. Okay. So they were close in G, but they are super far in G minus C1. It means what? It means that the length increase C1 here really increased the length of the flow path really a lot by like 9H. Right? So what I'm going to define is just I look at all this length increase and kind of go through the path, like look at the prefix of this path until the length increase is at most h, and call this node incident to the cut here where the total length increase is at most h is like x prefix, and do the same thing for x suffix. Okay. So you can see that this x suffix here is this x prefix here is still close to a, even in G minus C1. In G, they are close within H, but in G minus C1 is close within 2H because the total length increase here is just at most H. Okay. So A and X prefix is within distance like 2H, meaning that there must exist a router that contains A and X prefix, and the router that contains the similar thing, like there is a router that contains X suffix and B. So then the natural thing to do is like just try to route from A to X prefix and route from X suffix to B. Okay. So this basically kind of induce a new demand in this subpath. But this new demand is the demand on top of the cut. But that cut, this cut C1, is just how do we define A2, right? So what we do then, just recurse on the next level. You like from routing from A and B to X suffix and prefix. It induces a new demand that is even shorter because it's a subpath. It's the demand on the subpath. And suppose that A2 is now routable. There is a router on top of it. So just now you can just route on top of A2. So the point is, for each level, you can have pay 2 steps and 220 HS length. And that's why we get it. We get that the length slack is something like you get 2 T step here, and the slack is 20 SH ST, which is something like T square, and the congestion is n to the 1 over T. Okay. So I hope you see how to construct this. So I'm gonna finish in 2 minutes, sorry. So we can make this algorithmic. It's gonna be a bit like worse. Right now, we don't know how to match the trade-off we have for existence. It's a good problem, how to make it nice algorithmically. But for algorithmic version, you can build it in basically linear time, but with this poly edge factor. Okay, so so we learned 3 concepts, 3 pictures, right? Keep this in mind. When the node weighting A is routable, it means that there is a witness router on top that an embedding with good length and congestion. If it's not routable, it still exists expanded decomposition where you increase the length a bit, and then after length increase, it's routable. And you see how to build low step flow emulator. That is the core object in both like next 2 days. It's a graph simplification such that it basically preserves both length and congestion. And once you have it, just focus on flow with constant steps. Okay. Yeah. Hopefully we see you again tomorrow and next on Thursday. Thank you. Any question? Okay, we can take question offline. Thank you. Yeah.